All right, a heating curve is our way of tracking energy as a substance goes from one temperature to another, or from one temperature through a phase change to a different temperature, or to calculate the energy it takes to just do a phase change. So on the board here I've got how much energy is needed to heat 100 grams of ice that it's at negative 15 degrees Celsius to steam at 120 degrees Celsius. So this is going to happen in many different stages, and we're going to need to calculate each stage separately. So the first thing is I'm going to use this time and temperature graph to graph the changes that are occurring. So my ice is initially starting off at negative 15 degrees Celsius. When I add heat to that, the temperature is going to go up until I reach the melting point of water, which is 0 degrees Celsius. So literally what's happening during this portion of the graph, here's my ice cube. And in this ice cube, I've got water molecules that are arranged in an orderly, let me make those blue, that are arranged in an orderly configuration. And the intermolecular forces between these particles is strong. So they're locked in place. Now what they do have is they do have vibrational energy. So when I'm taking the ice from negative 15 degrees Celsius to 0 degrees Celsius, the only thing that's going to change is I'm going to have more vibrational energy. So I'm adding more lines here to show that these are vibrating more. So that's the only thing that's happening here. Remember, when we have a temperature change is a change in thermal energy, and that means that my particles are speeding up. The yellow lines are the intermolecular forces, the red lines. And these green lines are the vibrations. So when I'm going from negative 15 to 0, the only thing that's changing, adding energy, is going to increase the speed of the particles. Only. So it's speeding up, they're going faster, so there's an increase in thermal energy. So that's going up because my temperature is changing. So the only thing this energy is doing is changing the temperature of my sample. Now to calculate this, I'm going to be using Q equals mc delta T. So Q equals the energy. M will be the mass. In this case, the mass is going to be 100 grams. C equals the specific heat of water. Which will be given to you in a question. In this case, it's going to be 2.1 joules per gram per degree Celsius. And my delta T is the change in temperature. And in this case, I'm going from negative 15 to 0, which is a delta T of 15 degrees. Delta T's are always a positive value. You never put a negative number, because the change in temperature is 15 degrees. So the next thing I need to do is just substitute these numbers into my formula. I'm solving for the amount of energy. My mass is 100 grams. My C is 2.1 joules per gram per degree Celsius. And my delta T was 15 degrees Celsius. So my grams are canceling out, my degrees Celsius are canceling out, and my answer is going to be in units of joules. So we're going to call this Q1. Q1 will equal these numbers multiplied together. So Q1 will give you a calculator answer of 3150, and that'll be joules. Now at this stage, what I do is I go ahead and I look at my significant figures. I'm going to make this a decimal point just so I want to use two significant figures for my answer. So my Q1 is going to equal 3200 joules. And that's going to be the energy required to heat this ice from negative 15 degrees Celsius to 0 degrees Celsius. All right, now I'm ready for the next step. So I've taken this ice up to 0 degrees Celsius. Now I can't go straight up to 120 because once this hits 0 degrees Celsius, we're now going to have a phase change. So I'm now going to calculate this portion of the line, and we're going to call this Q2. Now what's happening in this portion of the line is I've got ice particles. Here's my ice particles that are in a very regular, orderly pattern, and the intermolecular forces between them is strong. Remember that I was increasing the vibrational energy as I increased the temperature, so these actually have a lot of vibrational energy. Now, at this stage here, the temperature is going to remain constant because what's going to happen is our molecules are going to change phase. We're going from an ice, this was ice, and we're going to liquid. Now, the intermolecular forces between the liquid particles are not as strong, so I'm drawing these with light lines that are a little bit lighter. Now, they have vibrational energy, but the connection between these particles is a lot less. Ice has low phase energy, and liquid has higher phase energy. So any of the energy that's added, so added energy, is being used to overcome the intermolecular forces. The force that's the force of attraction between ice particles and liquid particles is less. So that energy that's coming in at this point right here is being used to overcome that energy and turn it from solid to liquid. Notice that there's no temperature change. The particles are not speeding up. So there's no temperature change in this portion. So to calculate this, I'm going to need a different formula because now I don't have any change in temperature. I can't use Q equals mc delta T. So the formula I'm going to use for this section is Q is equal to mH of fusion. The process of melting or freezing is called fusion. So that's what's happening right here. So Q is going to equal the energy needed to do this. M is the mass of the substance. In this case, it's 100 grams. And my delta H would be given to, or my H of fusion would be given to you. And in this case, it's going to be 334 joules per gram. So I substitute these in. So Q equals M, H of fusion. My energy needed is going to be 100 times 334. And that's going to give you a Q2 equal to a calculator answer of. Now for this one here, I'm using the only number that came from my question is the 100 grams, and that has 3 significant figures. So my Q2 is going to be 334.00 joules. So that's going to be the answer for Q2. All right, so now I've calculated the first 2 portions of this heating curve, and I'm ready to go on to the next portion. Now, our next portion is going to take us from 0 degrees Celsius up to 100 degrees Celsius, because that's the boiling point of water. So I'm going to go all the way up from 0 to 100 for our next portion, and this will be Q3. So the energy needed to take this sample, which was 100 grams of what was originally ice, from now liquid water all the way up to its boiling point. Now, what's happening in the sample at this point is I've got my water molecules with intermolecular forces holding them together. They have a good amount of energy or particle movement. Now, the energy is going to be used to do 2 things. It's going to be increasing the distance between the particles a little bit. And it's also, these are still have intermolecular forces between them. It's also being used to increase the speed of these particles. So the more energy I put in, the distance between them is going to get farther, and the speed is going to get greater. So in this part here, we have energy added. Whoop, let me write that like an E. Is increasing the distance between particles and increasing the speed. Which means thermal energy is increasing. So I have a change in temperature. Now, to calculate this one, because I have a change in temperature, I'm going to need to use the formula Q equals mc delta T, because I have that change in temperature. Remember, Q is going to equal the energy needed. C is the specific heat. But this time we don't have ice anymore, we've got water. So the specific heat of water is 4.18 joules per gram per degree Celsius. And that will always be given to you in the question. My delta T here, or the change in temperature, we're going from 0 degrees Celsius to 100 degrees Celsius. So my delta T is going to be equal to 100. It's changing 100 degrees Celsius. Now I'm going to substitute these numbers into my formula and solve. I'm going to be solving for the energy. My mass was 100 grams. My C, or specific heat for water, is 4.18 418 joules per gram per degree Celsius, and my delta T was 100 degrees Celsius. Now, the delta T, I calculated that myself, so it's not going to go into figuring out my significant figures. So this will be Q3. So when I put that in the calculator, Q3 will be equal to, that'll be equal to a calculator answer of 41800. I'm going to need 3 significant figures because this number here is setting my significant figures, so that has the right number of significant figures. So there's my answer. So it's going to take 41,800 joules to take the water from 0 degrees to water at its boiling point of 100. Now in this next portion, I have to calculate how much energy it's going to take to boil the water. So I'm going to be calculating this section of the graph right here. This is going to be Q4. So what's happening at the molecular level here is I've got my water molecules with intermolecular forces between them. And they've got vibrational movement, and they're vibrating moving pretty fast and sliding past each other pretty fast. So I'm drawing 3. Now, what's going to be happening here, this is going to change too. Water molecules, as they go from having a connection to them to not having a connection to them. So they're being turned into gas molecules. So during this portion of the graph, we're literally breaking the connections between these molecules and freeing them so we have gas. So we're going to have particle speeds, trying to make it 3 for each, and I'm going to turn that into gas with no connection between the gas molecules, but the gas is initially going to have the same speed. So the energy that's being added is being used to break or overcome between the molecules. Now this is going to need to take a lot more energy. Now here we're in the liquid phase, and we're changing it to the gas phase. Of course, gas has a lot more phase energy, so we have an increase in phase energy as we add more energy to the substance. So we have an increase in phase energy at this part. Now the formula we're going to need to do this is going to be Q equals mH of vaporization. This process here is vaporization. And it doesn't matter if I'm vaporizing or if I'm condensing it. So this would be both processes. It's the same formula. Here if we have melting or freezing, it's the same formula. It just depends whether you're taking energy away or you're adding energy. So in this formula here, our Q is going to equal the energy needed. The M stands for the mass. In this case, it's still 100 grams. And now we need a number that's called the H of vaporization, or the heat of vaporization. And again, that's going to be given to you. In this case, for water, it's 2,260 joules per gram. So I'm going to substitute the numbers in my formula. So my energy is going to be equal to 100 grams times the heat of vaporization, and that's going to give my answer for Q4. Q4 will be equal to 226,000. And that'll be joules per gram. I'm going to check my significant figures. I need 3 significant figures in this answer because this one was the one that came from my question. So I've got 3 significant figures, and this will be my answer. So the amount of energy it's going to take to completely boil my 100 grams of water will be 226,000 joules of energy. All right, on to the next portion of my graph. I'm not quite done yet because the question tells me I have to take the ice to steam at 120 degrees Celsius. So now I have to calculate the last portion of my heating curve, which will be this section right here where everything has been turned to steam, and we're going to call this Q5. So what's happening at the molecular level in Q5 is I've got water molecules that are going from this state to this state. And of course, this is steam. This is going to start off at a certain speed. There's no connection between the molecules. And what we're doing is we're going to increase the speed of these molecules, and we'll also increase the distance between them if that's possible. If this is in a room, of course, increasing the distance between them is going to be very easy to do. So energy added is being used to speed up particles and increasing distance, if possible. Of course, with a gas, it's really going to end up increasing our pressure as it hits the sides of a container. So this will have an increase in temperature, in thermal energy, which means increase so we have an increase in temperature here. So the formula I'm going to need to use this is Q equals mc delta T again. The Q is going to be the amount of energy. M is going to be equal to the mass. Again, I'm starting with the same mass. Mass isn't created or destroyed. So I'm still going to be using 100 grams. And my delta T in this case, change in temperature, it's going from 100 degrees Celsius to 120 degrees Celsius, which means my delta T is going to be 20 degrees Celsius. So write my formula down and substitute in my numbers. The energy for Q5 is going to be equal to 100 times, now the I forgot the delta C, or sorry, the C. C for steam, which is the specific heat, is equal to 2.02 joules per gram per degree Celsius. And then my delta T. My units are canceling out. No more grams, no more degrees Celsius, so my unit is going to be in joules. Q5 is going to be equal to these 3 things multiplied together. And that's going to give me a calculator answer of 4,040. Now, the number 120 came from my question. So this right here is going to set my significant figures. There's two significant figures in 120. I need to be sure I have two significant figures here. So my answer should be Q5 will be equal to two significant figures, which would be 4.0 times 10 to the third joules. I could use the long form of this because I'm going to be adding these numbers together, but we'll leave it like this for now with two significant figures. So that's going to be... Now I'm ready to put this all together. So the question said how much energy is needed to heat 100 grams of ice that is at negative 15 degrees Celsius to steam at 120 degrees Celsius. So now I've done all the individual parts of this calculation. I've used Q equals mc delta T for the parts of the question where I had a temperature change. And I've used Q equals M, in this case it was H of fusion, Q equals M times the H of vaporization, so the same formulas for this part here. And now I'm ready to put everything together. So to figure out the total amount of energy, I'm going to need to add Q1 plus Q2 plus Q3 plus Q4 plus Q5. And that's going to equal the total amount of energy. So looking back at what we calculated, Q1 was a total amount of energy of Q2 took Q3 was equal to Q4 was equal to and Q5 was equal to 4.0 times 10 to the third joules, which would be equal to 4,000 joules. So the last thing to do is to add all these up. So when you add these numbers all together, you get 308,400 joules, and that's the amount of energy that it's going to take to go from negative 15 all the way up to 120 degrees Celsius with 100 grams of ice. Total amount of energy. So to summarize this, the first thing you need to do for any of these questions is to graph the questions you're answering. Only graph the parts of the heating curve that are needed for the question. If I have a question that is if water is cooling from 60 until all the water has been turned to ice, I'm going to do my time temperature graph, which is of course the energy added. And here's my temperature. And I'm going to start with where the question tells me. The question is how much energy would be needed to be removed from water that's cooling from 60 till all the water has been turned to ice. So I'm going to be starting at 60, and it's going to be cooling. Now it's not going to cool straight down to ice. At 0 degrees Celsius, I'm going to have a phase change. So I'm going to have this part here. So this means I'm going to have a Q1, and then I'm going to have a Q2. And I need to calculate those in that order. So for this first part of the graph, I've got a temperature change, so I'm going to use the formula Q equals mc delta T. For this next part, I don't have a temperature change, so I'm going to need Q equals M. In this case, it's freezing, so I'm going to need the H of fusion. Those two This will be Q1 and Q2. When I'm finished calculating those parts, I'm going to need to take Q1 and add it to Q2 to get the total amount of energy. So you're only graphing the parts of the question the part of the heating curve that you need for the question. Make sure you're starting where the question is telling you to start and just follow what happens, and don't skip over any phase changes that might happen. The second type of question you may have is where you've got an unknown. It may tell you you have a certain amount of energy. It may say you've got 15,000 joules of energy. And how much water? What's the mass of water that could be turned, or that could be warmed up 25 degrees? So we're dealing with water here, so our C would be equal to 4.18 joules per gram per degree Celsius. And it said to change the water by 20 degrees Celsius, so my delta T would be 20. So now I'm just going to solve for M. So sometimes the questions will actually give you the amount of energy, and you've just got to calculate for one of the other parts of the formula that's unknown. And so it would just be isolate your variable. So 4.18 joules per gram per degree Celsius to get rid of that. If I do that to this side, I need to divide that the other side. So I need to then get rid of the 20. If I do it to that side, I need to do that to this side. And now I'm ready to calculate. So it's going to be the 15,000 joules. My joules are going to cross off. My degrees Celsius are going to cross off. And I'm going to be left with a certain number of grams that will be equal to my mass. In this case, when you put it in the calculator, you're going to find that you get 179 grams of water would be the amount of water that you could change using that amount of energy. Significant figure-wise, I didn't really write the question down, but I said we're going to change it by 20. 20 has one significant figure, so my answer would be 200 grams of water would equal the mass.